Problem number 54, because I forgot to write down the problem number again. Never done that before. But it reads a 60 kilogram skier, drawn by this person. They're wearing a bunch of winter gear because it's cold outside. Starts at rest from the top of a ski slope at 65 meters high. If friction is a force of friction forces do negative 10.5 kilojoules, that's 10,500 joules, of work as she descends, how fast is she going at the bottom of the slope? So that's part A. We'll do that first. So this part's that matters. So yeah, height, work done by the friction in part A, final or V1 and V0. V0's its initial, the skier's initial, V1's what we're looking for. So I have all the variables given to us written over here. Some of them, like the works, are done by equations. So you can see those on there. I'll explain some of them as I get to them, but let's zoom in if you need those variables. But anyways, how fast is she going? So, conservation of energy, so mgh, gravitational potential, is going to equal her kinetic energy at the end, which is half mv1 squared, plus the work done by friction, which I just keep it as positive to make things easier. You could subtract the work done by friction, but subtract the negative makes it positive. 10,500 joules, which was 10.5 kilojoules. So pretty much V1 is going to equal the square root of 2 mgh minus VFA, or WFA, which is the work done by friction in part A, all divided by m. M's still in the square root. So you're going to get 33.17 meters per second is V1. So we found that part. Part B, now moving horizontally, the skier crosses a patch of soft snow where the mu in this part is equal to 0.2. If the patch is 82 meters wide and the average force of air resistance is 160 newtons, how fast is she going after crossing the patch? So the work of air on part B is going to be your 160, its average force, times the distance of 82. The work of the friction is going to be the 82, the distance, times, it's going to be mass times gravity, which will be force normal times mu, the kinetic thing, which is 82. So you'll get 82 times 60 times 9.81 times 0.2. I don't know what that number is because I just plug everything in later. So again, conservation of energy. So half mv1 squared, energy right here, is going to equal half mv2 squared plus the work done by friction in part B. I wrote that part A, but it should be part B. And I wrote that as A. That should be a B. I'm going to fix that. WFB and WFB. Plus the work done by air resistance in part B, which is WAB. So you do some little algebraic solving. V2 is going to equal the square root of 2 times, then this big quantity of 1/2 mv1 squared, minus the work of friction in part B, minus the work of air in part B, close that, divided by the mass. This is algebra. I could have messed up, but I don't think I did. Anyways, you get 18.47 meters per second when you throw that into your calculator. That was easy. Now part C, the skier hits a snowdrift, which is this little thing here that I do. It's kind of triangular. So hits a snowdrift, penetrates 2.5 meters into it before coming to a stop. What is the average force exerted on her? That snowdrift stops her. So part C, switch over this side. Her kinetic energy in part 2 is going to be equal to her energy at the end. So half mv2 squared is going to equal the work done by the drift, WD, which is going to equal the force over this distance times this distance. So you just try to divide each side by x. So half mv2 squared over x equals force of x, and you get 4,094 newtons. That was a fun problem.